We've heard already about how materials provide solutions for energy generation, for energy storage, energy recovery, and heating and cooling. But we now want to look at how we can use materials to reduce the energy losses in electronic devices. Next slide, please. If you look on the left-hand side here, you can see a whole range of things from the consumer products based on the transistor, the portable electronic devices we have, through to electric drives in vehicles, all the way through to the grid. And the electronics industry is enormous internationally, with over 600 billion pounds worth of markets. And similarly, the power electronics industry is over 100 billion pounds, and these are growing year on year. But one of the problems we have is, of course, with this growth comes energy usage. And already 5% of the world's energy is used in digital technologies, and this is expected to reach over 20% by 2030. And it's also notable that the UK has a relatively small component of that global electronic sector. So the question we're thinking about is, how do we stimulate the UK economy in the electronic sector? How do we meet consumers' expectations for bigger and better electronics? But at the same time, how do we meet the government's net zero greenhouse gas emission targets by 2050? Next slide, please. We undertook a road mapping with more than 50 participants, and with industry represented by the wafer fab companies, the equipment manufacturers, and by a series of end users. And we looked at research in 3 principal areas. Next slide, please. The first was power electronics, how we control the flow of electrical energy from the source, for example, wind energy or photovoltaics, through to load and where we use it, and the use of power electronics in things like electric vehicles. And the first thing that was really clear from the roadmaps was the need to find a way to take the excellent research done by academic institutions in the UK and scale this up. We need a pipeline for industrial exploitation through pilot lines, through to wafer scale and to manufacture. It's also clear that we need to be able to innovate in the current devices used for power electronics based on gallium nitride and silicon carbide materials. The right-hand figure just shows the advantage of moving from silicon to silicon carbide in wind generation and how you can reduce the power loss quite significantly just by that change of materials. But more importantly, we wanted to think about what was going to happen beyond gallium nitride, what was going to happen beyond silicon carbide. What were the next generation of materials for power electronics? What will we be using in 2050? And in doing that, we thought about the availability of materials and avoiding using materials that are scarce. We've already heard mention of gallium being one of those. How we recycle our electronics devices, and then how we look at the full energy cost of those devices, not only in the manufacturing stage, but also their whole life usage. Next slide, please. The second area we looked at was going beyond CMOS, the current technology we use in all our computers. If you look on the diagram on the right, we want to move to the bottom left-hand corner where we see the red star. And in order to do that, we looked at different things we could do with the transistors in terms of different variations of the channel and also the style of way that the transistor worked. But at the same time, we realized that as well, we could try and get CMOS to do more for ourselves by combining those transistors with things like sensing, energy harvesting, and RF devices. And that meant mixing the CMOS capability with things like photonic, magnetic, piezoelectric, plasmonic materials to get additional functionality with the devices we have now. So those are the first 2 areas we looked at in the road mapping exercise and things that have input on manufacture now. The third area, though, and this has been very well introduced by Professor Parkin this morning, next slide please, was what are we going to do beyond the current materials and devices we have? Going beyond CMOS into what's called more than Moore, beyond Moore's law, which has helped dictate what's happened in the computing industry up to now. And so we're looking for new architectures for computing, such as what goes on in the brain, neuromorphic computing. And the diagram on the left shows our desire to reduce the energy cost per bit, to make things more complicated, but as well minimize error rates. And in order to do that, we need to again move towards that red star on the bottom of the diagram on the right-hand side. But here we need to use different devices and different materials from conventional CMOS. So things like spintronic, topological, and organic materials, and use, as we heard earlier on, things like chargeless computational schemes and collective switching. Final slide, please. So if we think about where we are now, we have world-class scientists and engineers in the UK and some state-of-the-art facilities. Now we can take those and we can combine them with new approaches based on big data and artificial intelligence to materials discovery. We can look to add in piloting of new materials all the way through from fundamental research to wafer scale fabrication and manufacture. And then look at the real importance of materials recycling, testing and metrology. If we can put all that together in the UK, then we can deliver a transformative program to deliver on society's increasing energy demands, but reducing its carbon footprint. We can attract industrial investment into the UK and capitalize on our real strengths in advanced materials. And importantly, we can enable the UK to be the internationally leading innovator in the device supply chain for electronic devices and provide that sovereign capability for the UK. Thank you very much.